Welcome to Bright Ray Academy, where the future of radiology students will be as bright as rays. Chapter 5, the X-ray Imaging System. Get ready to take the literal controls of medical imaging today. We are cracking open the hood of the X-ray generation system, and we're going to take all those complex, abstract concepts of electrical physics and ground them into the tangible, everyday tools you'll be using to see right through the human body. Okay, let's dive right into this explainer.
And you know, I just had to say that quote right off the bat because I absolutely love our motto here. It sets the exact right tone for this chapter. For all you future technologists out there, mastering this foundational physics is really what separates the button pushers from true clinical experts. You are the ones who will wield this incredible technology safely and effectively.
Here is our roadmap for today. First, we'll look inside the operating console. Next, powering up with the Autotransformer. Then, controlling beam quality with Kilovololt Peak and beam quantity with Milliamperage. Finally, we'll wrap up with exposure timers and AEC.
All right, Section 1, inside the operating console. This right here is your daily workspace. It's where the magic happens. Think of the operating console as your cockpit. It's what allows you, the radiologic technologist, to control the X-ray tube current and voltage. Now, keep in mind, an X-ray tube operates at massively high voltages. We're talking kilovolts here, and obviously you do not want to be standing anywhere near those raw, dangerous power levels, right? That's exactly why all the electric circuits connecting to these meters and controls operate at a very low voltage. It's just a brilliant piece of engineering, specifically designed to minimize any possibility of a hazardous electrical shock while you're working.
So, the really crucial thing to understand is what exactly you're adjusting from that safe, low-voltage cockpit. It basically boils down to two distinct concepts, quantity and quality. Radiation quantity, that refers to the pure intensity, the actual number of X-rays in the beam. We control this with milliamperage or MA. Radiation quality, on the other hand, refers to the penetrability, or the overall energy of that X-ray beam. Like, can it pass through dense bone or just soft tissue? That is determined by the kilovolt peak or kVp. Simply put, quantity is how many, quality is how strong.
Moving on to Section 2, powering up, the Autotransformer.
Okay, so the power supplied to your imaging system, it gets delivered first to the Autotransformer. Now, unlike conventional transformers that have two separate coils of wire, the Autotransformer is actually really unique. It has only a single winding of wire and just one core. It works on this principle of electromagnetic self-induction. And you might be wondering, why do we use it? Well, because it is infinitely safer and way easier to take a low voltage, control it precisely, and then step it up to massive kilovolt levels rather than trying to tame some massive voltage after it's already been created. Makes perfect sense, right?
And that brings us to the Autotransformer law. Now, I know it might look like complex math at first glance, but honestly, it's wonderfully simple in practice. It basically just states that the voltage it receives, the primary voltage, and the voltage it provides, the secondary voltage, are directly related to the number of turns of the transformer enclosed by their respective connections. So just by tapping into different sections of that one single coil of wire, the system can precisely select the exact voltage it needs to send down the line.
Take a look at how the primary connections on the left tap into the winding, while the secondary connections on the right can be adjusted to encompass more or fewer coils. This one single component acts like the grand distributor for the whole system. It supplies a really precise, carefully varied voltage to both the filament circuit, which we'll get into in a second, and the high voltage circuit, which is what creates the actual X-rays.
All right, Section 3, Kilovolt Peak, beam quality.
Whenever you select a kVp on your console, what you are actually doing is selecting a specific series of connections on that exact Autotransformer we just looked at. Fun fact, older systems literally had two physical knobs, major kVp and minor kVp. The major knob made these big jumps, and the minor knob lets you fine-tune the technique. Today, of course, it's largely digital, but the underlying physics are exactly the same. Also, your console features a pre-reading kVp meter. This is absolutely crucial because it lets you monitor the exact voltage you're going to use before you even press the exposure button. No guesswork at all, just pure precision.
Next up, Section 4, Milliamperage beam quantity.
Now, to really understand the beam quantity, you have to understand thermionic emission. Inside the X-ray tube, there's a tiny coil of wire called a filament. It's actually kind of similar to the coils inside a regular kitchen toaster. When current runs through it, it gets incredibly hot. But instead of toasting bread, this intense heat actually boils off outer shell electrons. This release of electrons, that is thermionic emission.
The hotter the filament gets, and it normally operates at a current of about 3 to 6 amperes, the more electrons are released, and ultimately, the more X-rays are produced. Let's connect these two systems together. Power flows from the autotransformer on the left right across into the filament circuit on the right. Here, precision resistors drop the voltage to match your selected MA station. It then hits a step-down transformer. Now, this is distinct from the main high-voltage transformer. This step-down transformer drops the voltage down to about 12 volts, but bumps the current way up to 5 to 8 amperes. Why? To safely and effectively heat up that filament.
Okay, but as perfectly separated as these circuits might seem, they actually interact in some pretty sneaky ways. Enter the space charge effect. Here's what happens. As you raise your kVp to get a more penetrating beam, the anode side of the tube becomes highly attractive. So much so that it actually starts pulling extra electrons across the tube that normally wouldn't have even had the energy to leave the immediate area of the filament. So raising your kVp accidentally increases your MA. To stop this from happening, modern systems actually have a built-in correction circuit to counteract the space charge effect, ensuring your selected MA stays perfectly stable.
Ultimately, the total quantity of radiation hitting the image receptor isn't just about the tube current. It's about how long you actually let that current flow. The product of X-ray tube current, which is MA, and exposure time in seconds gives us MAS. This represents the total electrostatic charge, and it is the primary controller of the final optical density of your image. Higher MAS means more X-rays, which means a darker image. It's a simple but absolutely vital equation.
And finally, Section 5, Exposure Timers and AEC.
So the timing circuit is actually completely separate from the other main circuits, and it usually operates on the safer primary side of the high-voltage transformer. First off, there is a built-in safety net called a guard timer. This will forcefully terminate any exposure after about 6 seconds, just ensuring you can literally never accidentally irradiate a patient continuously. But for your actual exposures, we have incredibly accurate options capable of intervals as tiny as 1 millisecond. While older systems use these motor-driven synchronous timers, modern equipment relies on microsecond-fast electronic timers, or MAS timers. These are specially designed to calculate the highest safe tube current for the shortest possible time to hit your desired MAS target, which really helps reduce patient motion blur.
But listen, even with the most precise electronic timers in the world, human bodies are incredibly variable. A dense chest is very different from a highly aerated one. So what actually takes the guesswork out of patient exposure time?
The answer to that is automatic exposure control, or AEC. Instead of you just guessing the time, the AEC measures the actual X-ray intensity after it passes through the patient right at the image receptor. It typically uses these flat radiolucent ionization chambers positioned between the patient and the receptor. Once that chamber detects that the exact right amount of radiation has been reached to create an optimal image density, it instantly sends a signal to break the circuit and terminate the exposure. It's basically automated precision.
It's also really worth noting that the efficiency of these timers depends heavily on your system's power generator. If you want a quick way to identify how powerful a system is, just look at its shortest possible exposure time. Older single-phase generators are pretty limited. They can't physically produce an exposure shorter than about 8 milliseconds. But modern three-phase and high-frequency generators, they use advanced voltage rectification to create a nearly constant potential. This minimizes what we call voltage ripple, maximizing the system's power rating and making the beam vastly more efficient. You also have specialized systems like capacitor discharge generators that store power for portable exams. But in the main room, some modern generators use falling load logic to automatically start at the highest MA and drop as the anode heats up. This allows for those ultra-crisp, 1 millisecond exposures that are absolutely essential for capturing moving anatomy, like a beating heart.
Which brings us to our final thought. We've explored autotransformers, precise kilovolt adjustments, space charge correction circuits, and microsecond timers. Today's systems literally do the heavy mathematical lifting for you. So, as automated features like AEC and falling load generators handle the math, how exactly does your role evolve? Well, I'll leave you with this. The machine knows the physics, but it absolutely does not know the patient. Your role shifts from mere calculation to true clinical mastery. It's about proper patient positioning, adapting to unique pathologies, and knowing exactly when to trust the automation and when to override it. That's what makes your future as bright as Ray's. Thank you so much for joining me for this explainer, and keep learning.